The advanced microscopy facilities of DISAT perform imaging and morphological, structural and chemical characterization of various materials. Our equipment consists of atomic force microscope, nano-infrared microscope, scanning electron microscope, transmission electron microscope, scanning tunneling microscope and focused ion beam. Our microscopes operate at microscale, nanoscale, and atomic scale. Microscale refers to objects having size ranging from several hundreds of nanometers to tens of micrometers. This is the scale of the structures of living tissues, composite materials, and microelectromechanical devices. Microscale imaging is important for cellular biology, materials and electronic engineering, environmental analysis, forensics, and so on. Microscale imaging can be performed at Polytechnico by means of atomic force microscopy, nano-infrared microscopy, and scanning electron microscopy on very different types of samples. The atomic force microscope mode allows constructing three-dimensional topography maps of the surface with a much higher resolution than that possible with optical microscopes. AFM also maps the local mechanical, electric and thermal properties. Nano-IR combines AFM with an infrared laser hitting the sample. It maps the thermal and infrared optical properties and discriminates between different chemical structures. In SEM, a focused beam of electrons scans the surface of a sample while various detectors collect scattered electrons and X-rays emitted from the sample. A 2D image of the sample is generated bringing information on its morphology and composition. Nanoscale refers to objects having size ranging from few nanometers to few hundred nanometers. These are the typical sizes of cellular structures and subcellular components. Moreover, at this scale many materials exhibit interesting and peculiar properties that they do not display at larger scales. For this reason, nanostructured materials, nanoparticles, nanocrystals, are nowadays exploited in innovative technologies including nanoelectronics, catalysis of important chemical reactions, biomarkers and biosensors, development of targeted therapies, and theranostics. Nanoscale imaging can be performed by means of AFM, nano-IR, SEM, and SEM-focused ion beam. At this scale, AFM and nano-IR can be employed, provided that the samples exhibit a roughness of the order of few tens of nanometers at most. At this scale, nano-IR can be employed to map local chemical composition below the diffraction limit of light, and to perform nanoscale topographic, mechanical and thermal analyses. SEM-FIB couples the focused electron beam of SEM with a focused ion beam, which can be used for analogous characterizations and also, thanks to the larger mass of the ions, can be used to locally dig or cut a sample according to any desired pattern with nanometric precision. FIB can make a local deposition of material whose size, shape and thickness can be tailored on demand. Its high-energy ion beam can be used to dig trenches, cut out thin sections and, thanks to an incorporated nanomanipulator, portions of sample can be transferred to another substrate for further analysis. At this scale, AFM allows mapping local mechanical, thermal and electrical properties below the diffraction limit of light. Atomic scale refers to the scale at which single atoms become visible, which means from few nanometers down to typically 0.1 nanometers. In this domain, microscopy aims at looking at the regular arrangement of atoms in the crystalline structure, at the presence of defects and distortions, and at interfaces between different phases, materials, or crystalline structures. Atomic scale imaging can be performed by means of transmission electron microscopy and scanning tunneling microscopy. TEM generates a beam of high-energy electrons that cross the sample and are collected after it, carrying information on its structure and composition, while STM is based on quantum mechanical tunneling and allows directly imaging of the electronic density and a 3D map of the sample topography.